Alright, in the last video we talked about vectors, and they have a magnitude and a direction. And this time I want to talk about vector components. If we are talking about somebody's pushing on, pushing on an object with a force of, let's say, 10 newtons, but it's at this angle. It makes it hard if I have another vector like this and I want to add them together. It makes it very difficult. If they're all in a straight line, no problem. But when you have them at an angle, then we have an issue. So what's convenient to do is to consider a grid here. Here's my x, here's my y. And to break things up, I'll find out how much this goes in the x direction, how much of this goes in the y direction. And if I take, let me call this vector A. Okay, if I had a whole bunch of vectors A, B, C, A plus B plus C, I could say the x direction of the resulting vector would be the x component, how much the A vector goes in the x direction, how much of the B vector goes in the x direction, how much the C vector goes in the x direction. And there's something I haven't really talked about, which is notation. And the notation of a vector is generally we have either it's in bold, you'll see it in print, or you have a little arrow over it. And I need to start doing that now. Okay. And similarly, for the y direction of the resultant would be the sum of all the y directions. And this just makes sense. This one pushes this much in the x direction. If I add up how much this pushes in the x direction plus how much the b one pushes in the x direction and so forth, we can add these together. So this is just a very convenient way. If we can figure out how far it's pushing that way, how hard it's pushing that way, it makes it very convenient to add these vectors together. So we need to figure out how to do that. Let me slide this up and let's look at, I'll take this guy here. I'm going to make it like that. I'm going to make it fairly large. And I'll say this is 50 newtons. And let's say this angle, we do need to know the angle. The angle with the x-axis, let's say it's 30 degrees, and I don't think I drew that very well as a 30-degree angle. Okay, if we want to find out this component, how much it goes this way, all we have to do is use trigonometry. And so trigonometry would tell us that the hypotenuse, 50 newtons, times the cosine of 30 degrees would give us this component, how much it goes this way. And you can see visually, this was just going to line up. This makes a triangle, a right triangle. Similarly, this portion here, which would be the y component, and customarily we'll draw it like this because we could put it either place, but this is going to be 50 sine of 30 degrees. Okay. And I know sine of 30 degrees is 0.5. Again, I didn't draw the angle very well. This would end up being 25 newtons. I'm being lazy. I'm leaving out my units. Okay, and this one would end up being 43.3 newtons. So what this allows me to do is if I have several of these and I've broken them all down, let me do another one here, and let me use 60 degrees just because it's easy for me. Well, I'll use 45 degrees. I know that one. So 45 degrees, I'm going to use 20 at an angle of 45 degrees. And it looks like it could be 20. And when I break that down, I get a component of 20 times the cosine of 45 would be 14.14 newtons. And in the y direction, it would also be 14.14 newtons, just because of that whole business of sine and cosine of 45 being the same. So if I want to find out if both of these guys push together, and I draw that tip to tail. Don't always have to draw this, by the way, but I think it's useful. Then you can see the x component at the end, and I'm going to need a different marker for this one. The x component of the sum of these two. I kind of wish I had a better marker for that. Okay, I'm just going to stick with the black then. Let me just draw it like this. The x component of the sum of those is going to be 43.3 plus 14.14. And then the y component is going to be 25 plus 14.14. Let me draw that down here. Okay. So the y component, 25 plus 14.14 is 39.14 newtons. And then over here, the x component is 43.3 plus 14.14, which ends up being 57.44 newtons. Okay, but that doesn't help me so much. I know, okay, it's going up and it's going to the right. But we want to find out what the final resultant is. Well, we can add these together. Boom. Goes up and to the right that much. It makes kind of a rectangle there. To find this, and let me call this C. This is going to be my sum. My C vector is going to be my sum. To find this, once again, this just makes a right angle. We can think of it like this. 57.44, 39.14. And so the magnitude of C, the size of C, and we write that like this. Magnitude of C. It's just like the absolute value sign. Is just going to be the square root of 57.44 squared plus 39.14 newtons squared. Again, I'm screwing up my symbols there, my units. And the angle, I'll call this theta prime. Theta prime is going to be the inverse tangent, arctangent, of 39.14 newtons divided by 57.44 newtons. So the big relationships, and we do this an awful lot, you're going to see this over and over. The big relationships are to find components. I'll say A sub x is going to be A times the cosine of theta. And actually I can write that as magnitude of A times the cosine of theta. A sub y is going to be, I really need to make these magnitudes also. The size of the y component is going to be the size of a vector times the sine of the angle. And then we're combining components. To combine components, let me just say A, the magnitude of A, is going to be square root of the magnitude of A sub x squared plus A sub y squared. And the angle theta is going to be the inverse tangent of A sub y over A sub x. Those are magnitudes. Boy, I've got to get my notation right on all those. Okay, so that's how we break things down and recombine after we've added them together. And you're going to see this over and over. We do this so often, particularly when we get to, well, certainly when we get to forces and when we get to fields, electric fields, and so forth.